JEP 453, Structured Concurrency, Preview. Summary: simplify concurrent programming by introducing an API for structured concurrency. Structured concurrency treats groups of related tasks running in different threads as a single unit of work, thereby streamlining error handling and cancellation, improving reliability, and enhancing observability. This is a preview API. History: structured concurrency was proposed by JEP 428 and delivered in JDK 19 as an incubating API. It was re-incubated by JEP 437 in JDK 20 with a minor update to inherit scoped values, JEP 429. We here propose to make structured concurrency a preview API in the java.util.concurrent package. The only significant change is that the structured task scope :fork method returns a subtask rather than a future, as discussed below. Goals: 1. Promote a style of concurrent programming that can eliminate common risks arising from cancellation and shutdown, such as thread leaks and cancellation delays. 2. Improve the observability of concurrent code. Non-goals: 1. It is not a goal to replace any of the concurrency constructs in the java.util.concurrent package, such as executor service and future. 2. It is not a goal to define the definitive structured concurrency API for the Java platform. Other structured concurrency constructs can be defined by third-party libraries or in future JDK releases. 3. It is not a goal to define a means of sharing streams of data among threads, i.e., channels. We might propose to do so in the future. 4. It is not a goal to replace the existing thread interruption mechanism with a new thread cancellation mechanism. We might propose to do so in the future. Motivation: developers manage complexity by breaking tasks down into multiple subtasks. In ordinary single-threaded code, the subtasks execute sequentially. However, if the subtasks are sufficiently independent of each other, and if there are sufficient hardware resources, then the overall task can be made to run faster, i.e., with lower latency, by executing the subtasks concurrently. For example, a task that composes the results of multiple I/O operations will run faster if each I/O operation executes concurrently in its own thread. Virtual threads, JEP 444, make it cost-effective to dedicate a thread to every such I/O operation, but managing the huge number of threads that can result remains a challenge. Unstructured concurrency with executor service. The java.util.concurrent.executor service API, introduced in Java 5, helps developers execute subtasks concurrently. For example, here is a method, handle, that represents a task in a server application. It handles an incoming request by submitting two subtasks to an executor service. One subtask executes the method findUser and the other subtask executes the method fetchOrder. The executor service immediately returns a future for each subtask, and executes the subtasks concurrently according to the scheduling policy of the executor. The handle method awaits the subtasks' results via blocking calls to their futures get methods, so the task is said to join its subtasks. Response handle throws execution exception, interrupted exception, future string user equals esp.submit, greater than find user, future integer order equals esp.submit, greater than fetch order, string the user equals user.get, / join find user. Int the order equals order.get, / join fetch order. Return new response the user, the order. Because the subtasks execute concurrently, each subtask can succeed or fail independently. Failure, in this context, means to throw an exception. Often, a task such as handle should fail if any of its subtasks fail. Understanding the lifetimes of the threads can be surprisingly complicated when failure occurs. 1. If findUser throws an exception, then handle will throw an exception when calling user.get, but fetchOrder will continue to run in its own thread. This is a thread leak which, at best, wastes resources. At worst, the fetchOrder thread will interfere with other tasks. 2. If the thread executing handle is interrupted, the interruption will not propagate to the subtasks. Both the find user and fetch order threads will leak, continuing to run even after handle has failed. 3. If find user takes a long time to execute, but fetch order fails in the meantime, then handle will wait unnecessarily for find user by blocking on user.get rather than cancelling it. Only after find user completes and user.get returns will order.get throw an exception, causing handle to fail. In each case, the problem is that our program is logically structured with task-subtask relationships, but these relationships exist only in the developer's mind. This not only creates more room for error, but it makes diagnosing and troubleshooting such errors more difficult. Observability tools such as thread dumps, for example, will show handle, find user, and fetch order on the call stacks of unrelated threads, with no hint of the task-subtask relationship. We might attempt to do better by explicitly cancelling other subtasks when an error occurs, for example by wrapping tasks with try finally and calling the cancel boolean methods of the futures of the other tasks in the catch block for the failing task. We would also need to use the executor service inside a try with resources statement, as shown in the examples in JEP 425, because future does not offer a way to wait for a task that has been cancelled. But all this can be very tricky to get right, and it often makes the logical intent of the code harder to discern. Keeping track of the inter-task relationships, and manually adding back the required inter-task cancellation edges, is asking a lot of developers. This need to manually coordinate lifetimes is due to the fact that executor service and future allow unrestricted patterns of concurrency. There are no constraints upon, or ordering of, any of the threads involved. One thread can create an executor service, a second thread can submit work to it, and the threads which execute the work have no relationship to either the first or second thread. Moreover, after a thread has submitted work, a completely different thread can await the results of execution. Any code with a reference to a future can join it, i.e., await its result by calling get, even code in a thread other than the one which obtained the future. In effect, a subtask started by one task does not have to return to the task that submitted it. It could return to any of a number of tasks, or even none. Because executor service and future allow for such unstructured use, they do not enforce or even track relationships among tasks and subtasks, even though such relationships are common and useful. Accordingly, even when subtasks are submitted and joined in the same task, the failure of one subtask cannot automatically cause the cancellation of another. In the above handle method, the failure of fetch order cannot automatically cause the cancellation of find user. The future for fetch order is unrelated to the future for find user, and neither is related to the thread that will ultimately join it via its get method. Rather than ask developers to manage such cancellation manually, we want to reliably automate it. Task structure should reflect code structure. In contrast to the freewheeling assortment of threads under executor service, the execution of single-threaded code always enforces a hierarchy of tasks and subtasks. The body block of a method corresponds to a task, and the methods invoked within the block correspond to subtasks. An invoked method must either return to, or throw an exception to, the method that invoked it. It cannot outlive the method that invoked it, nor can it return or throw an exception to a different method. Thus all subtasks finish before the task. Each subtask is a child of its parent, and the lifetime of each subtask relative to the others and to the task is governed by the syntactic block structure of the code. For example, in this single-threaded version of handle, the task-subtask relationship is apparent from the syntactic structure. Response handle throws IO exception, string the user equals find user, int the order equals fetch order, return new response the user, the order. We do not start the fetch order subtask until the find user subtask has completed, whether successfully or unsuccessfully. If find user fails, then we do not start fetch order at all, and the handle task fails implicitly. The fact that a subtask can return only to its parent is significant. It implies that the parent task can implicitly treat the failure of one subtask as a trigger to cancel other unfinished subtasks and then fail itself. In single-threaded code, the task-subtask hierarchy is reified in the call stack at runtime. We thus get the corresponding parent-child relationships, which govern error propagation, for free. When observing a single thread, the hierarchical relationship is obvious: find user, and later fetch order, appear subordinate to handle. This makes it easy to answer the question, what is handle working on now? Concurrent programming would be easier, more reliable, and more observable if the parent-child relationships between tasks and their subtasks were evident from the syntactic structure of the code and also reified at runtime, just as for single-threaded code. The syntactic structure would delineate the lifetimes of subtasks and enable a runtime representation of the inter-thread hierarchy, analogous to the intra-thread call stack. That representation would enable error propagation and cancellation as well as meaningful observation of the concurrent program. The Java platform already has an API for imposing structure on concurrent tasks, namely java.util.concurrent.forkjoinPool, which is the execution engine behind parallel streams. However, that API is designed for compute-intensive tasks rather than tasks which involve I/O. Structured concurrency. Structured concurrency is an approach to concurrent programming that preserves the natural relationship between tasks and subtasks, which leads to more readable, maintainable, and reliable concurrent code. The term structured concurrency was coined by Martin Sestrike and popularized by Nathaniel J. Smith. Ideas from other languages, such as Erlang's hierarchical supervisors, inform the design of error handling in structured concurrency. Structured concurrency derives from the simple principle that if a task splits into concurrent subtasks, then they all return to the same place, namely the task's code block. In structured concurrency, subtasks work on behalf of a task. The task awaits the subtask's results and monitors them for failures. As with structured programming techniques for code in a single thread, the power of structured concurrency for multiple threads comes from two ideas: 1. Well-defined entry and exit points for the flow of execution through a block of code, and 2. A strict nesting of the lifetimes of operations in a way that mirrors their syntactic nesting in the code. Because the entry and exit points of a block of code are well-defined, the lifetime of a concurrent subtask is confined to the syntactic block of its parent task. Because the lifetimes of sibling subtasks are nested within that of their parent task, they can be reasoned about and managed as a unit. Because the lifetime of the parent task is, in turn, nested within that of its parent, the runtime can reify the hierarchy of tasks into a tree that is the concurrent counterpart of the call stack of a single thread. This allows code to apply policies, such as deadlines, to an entire subtree of tasks, and allows observability tools to present subtasks as subordinate to their parent tasks. Structured concurrency is a great match for virtual threads, which are lightweight threads implemented by the JDK. Many virtual threads share the same operating system thread, allowing for very large numbers of virtual threads. In addition to being plentiful, virtual threads are cheap enough to represent any concurrent unit of behavior, even behavior that involves I/O. This means that a server application can use structured concurrency to process thousands or millions of incoming requests at once. It can dedicate a new virtual thread to the task of handling each request, and when a task fans out by submitting subtasks for concurrent execution, then it can dedicate a new virtual thread to each subtask. Behind the scenes, the task-subtask relationship is reified into a tree by arranging for each virtual thread to carry a reference to its unique parent, similar to how a frame in the call stack refers to its unique caller. In summary, virtual threads deliver an abundance of threads. Structured concurrency can correctly and robustly coordinate them, and enables observability tools to display threads as they are understood by the developer. Having an API for structured concurrency in the JDK will make it easier to build maintainable, reliable, and observable server applications. Description: the principal class of the Structured Concurrency API is Structured Task Scope in the java.util.concurrent package. This class allows developers to structure a task as a family of concurrent subtasks, and to coordinate them as a unit. Subtasks are executed in their own threads by forking them individually and then joining them as a unit and, possibly, cancelling them as a unit. The subtask's successful results or exceptions are aggregated and handled by the parent task. Structured task scope confines the lifetimes of the subtasks to a clear lexical scope in which all of a task's interactions with its subtasks, forking, joining, cancelling, handling errors, and composing results, takes place. Here is the handle example from earlier, written to use structured task scope. Shutdown on failure is explained below. Response handle throws execution exception, interrupted exception, try, var scope equals new structured task scope dot shutdown on failure. Supplier string user equals scope dot fork, greater than find user, supplier integer order equals scope dot fork, greater than fetch, order. Scope dot join / join both subtasks. Throw if failed, / and propagate errors, / here, both subtasks have succeeded, so compose their results. Return new response user.get, order.get. In contrast to the original example, understanding the lifetimes of the threads involved here is easy. Under all conditions their lifetimes are confined to a lexical scope, namely the body of the try with resources statement. Furthermore, the use of structured task scope ensures a number of valuable properties. 1. Error handling with short-circuiting. If either the find user or fetch order subtasks fail, the other is cancelled if it has not yet completed. This is managed by the shutdown policy implemented by shutdown on failure. Other policies are possible. 2. Cancellation propagation. If the thread running handle is interrupted before or during the call to join, both subtasks are cancelled automatically when the thread exits the scope. 3. Clarity. The above code has a clear structure. Set up the subtasks, wait for them to either complete or be cancelled, and then decide whether to succeed, and process the results of the child tasks, which are already finished, or fail, and the subtasks are already finished, so there is nothing more to clean up. 4. Observability. A thread dump, as described below, clearly displays the task hierarchy, with the threads running find user and fetch order shown as children of the scope. Structured task scope is a preview API, disabled by default. To use the structured task scope API you must enable preview APIs, as follows. 1. Compile the program with Javac release 21 enable preview main.java and run it with Java enable preview main, or 2. When using the source code launcher, run the program with Java source 21 enable preview main.java, or 3. When using shell, start it with shell enable preview. Using structured task scope, the structured task scope API is public class structured task scope less than T implements auto, closable. Public U extends T subtask less than U fork callable less than extends U task, public void shutdown. Public structured task scope less than T join throws interrupted exception. Public structured task scope less than T join until instant deadline, throws interrupted exception, timeout exception, public void close. Protected void handle complete subtask less than extends T handle, protected final void ensure, owner, and joined. The general workflow of code using structured task scope is 1. Create a scope. The thread that creates the scope is its owner. 2. Use the fork callable method to fork subtasks in the scope. 3. At any time, any of the subtasks, or the scope's owner, may call the scope's shutdown method to cancel unfinished subtasks and prevent the forking of new subtasks. 4. The scope's owner joins the scope, i.e., all of its subtasks, as a unit. The owner can call the scope's join method to wait until all subtasks have either completed, successfully or not, or been cancelled via shutdown. Alternatively, it can call the scope's join until java.time.instant method to wait up to a deadline. 5. After joining, handle any errors in the subtasks and process their results. 6. Close the scope, usually implicitly via try with resources. This shuts down the scope, if it is not already shut down, and waits for any subtasks that have been cancelled but not yet completed to complete. Each call to fork starts a new thread to execute a subtask, which by default is a virtual thread. A subtask can create its own nested structured task scope to fork its own subtasks, thus creating a hierarchy. That hierarchy is reflected in the code's block structure, which confines the lifetimes of the subtasks. All of the subtasks' threads are guaranteed to have terminated once the scope is closed, and no thread is left behind when the block exits. Any subtask in a scope, any subtasks in a nested scope, and the scope's owner can call the scope's shutdown method at any time to signify that the task is complete, even while other subtasks are still executing. The shutdown method interrupts the threads that are still executing subtasks, and causes the join or join until instant method to return. All subtasks should, therefore, be written in a way that is responsive to interruption. A new subtask that is forked after a call to shutdown will be in the unavailable state and will not be run. In effect, shutdown is the concurrent analog of the break statement in sequential code. Calling either join or join until instant within a scope is mandatory. If a scope's block exits before joining, then the scope will wait for all subtasks to terminate and then throw an exception. It is possible for a scope's owning thread to be interrupted either before or while joining. For example, it could be a subtask of an enclosing scope that has been shut down. If this occurs, then join and join until instant will throw an exception because there is no point in continuing. The try with resources statement will then shut down the scope, which will cancel all the subtasks and wait for them to terminate. This has the effect of automatically propagating the cancellation of the task to its subtasks. If the join until instant method's deadline expires before either the subtasks terminate or shutdown is called, then it will throw an exception and, again, the try with resources statement will shut down the scope. When join completes successfully, then each of the subtasks has either completed successfully, failed, or been cancelled because the scope was shut down. Once joined, the scope's owner handles failed subtasks and processes the results of subtasks that completed successfully. This is typically done by the shutdown policy, see below. The result of a task that completed successfully can be obtained with the subtask.get method. The get method never blocks, it throws an illegal state exception if it is mistakenly called before joining or when the subtask has not completed successfully. Subtasks forked in a scope inherit scoped value bindings, JEP 446. If a scope's owner reads a value from a bound scoped value, then each subtask will read the same value. If a scope's owner is itself a subtask of an existing scope, i.e., it was created as a forked subtask, then that scope becomes the parent of the new scope. Scopes and subtasks thus form a tree. The structured use of structured task scope is enforced at runtime. For example, attempts to call fork callable from a thread that is not in the tree hierarchy of the scope, i.e., the owner, the subtasks, and subtasks in nested scopes, subtasks, will fail with an exception. Using a scope outside of a try with resources block and returning without calling close, or without maintaining the proper nesting of close calls, may cause the scope's methods to throw a structure violation exception. Structured task scope enforces structure and order upon concurrent operations. Thus it does not implement the executor service or executor interfaces, since instances of those interfaces are commonly used in a non-structured way, see below. However, it is straightforward to migrate code that uses executor service but would benefit from structure to use structured task scope. In practice, most uses of structured task scope will not utilize the structured task scope class directly, but rather use one of the two subclasses described in the next section that implement shutdown policies. In other scenarios, users will likely write their own subclasses to implement custom shutdown policies. Shutdown policies. When dealing with concurrent subtasks, it is common to use short-circuiting patterns to avoid doing unnecessary work. Sometimes it makes sense, for example, to cancel all subtasks if one of them fails, i.e., invoke all, or, alternatively, if one of them succeeds, i.e., invoke any. Two subclasses of structured task scope, shutdown on failure and shutdown on success, support these patterns with policies that shut down the scope when the first subtask fails or succeeds, respectively. Shutdown policies additionally provide centralized methods for handling exceptions and, possibly, successful results. This is in line with the spirit of structured concurrency, according to which an entire scope is treated as a unit. Here is a structured task scope with a shutdown on failure policy, used also in the handle example above, that runs a collection of tasks concurrently and fails if any one of them fails. T-list less than T-run all list callable less than T tasks, throws interrupted exception, execution exception, try, var scope equals new structured task scope dot shutdown on failure. List less than extend supplier less than T suppliers equals tasks dot stream. Map scope fork. To list, scope dot join throw if failed, / propagate exception if any subtask fails. / here, all tasks have succeeded, so compose their results. Return suppliers dot stream. Map supplier get. 2. List. Here is a structured task scope with a shutdown on success policy that returns the result of the first successful subtask. TT race list callable less than T tasks, instant deadline, throws interrupted exception, execution exception, timeout exception, try, var scope equals new structured task scope dot shutdown on success less than T, 4, var task, tasks, scope dot fork task. Return scope dot join until deadline result, / throws if none of the subtasks completed successfully. As soon as one subtask succeeds, this scope automatically shuts down, cancelling unfinished subtasks. The task fails if all of the subtasks fail or if the given deadline elapses. This pattern can be useful in, for example, server applications that require a result from any one of a collection of redundant services. While these two shutdown policies are provided out of the box, developers can create custom policies that abstract other patterns, see below. Processing results. After joining and centrally processing exceptions via the shutdown policy, for example, with shutdown on failure throw if failed, the scope's owner can process the results of the subtasks using the subtask objects returned from the calls to fork, if they are not processed by the policy, for example, by shutdown on success result. Typically, the only subtask method that a scope owner will invoke is the get method. All other subtask methods will ordinarily be used only in the implementation of the handle complete method of custom shutdown policies, see below. In fact, we recommend that variables referencing a subtask returned by fork be typed as, for example, supplier string rather than subtask string, unless, of course, you opt to use var. If the shutdown policy itself processes subtask results, as in the case of shutdown on success, then the subtask objects returned by fork should be avoided altogether, and the fork method treated as if it returned void. Subtasks should return as their result any information that the scope owner should process after centralized exception handling by the policy. If the scope owner processes subtask exceptions to produce a composite result, rather than use a shutdown policy, then exceptions can be returned as values from the subtasks. For example, here is a method that runs a list of tasks in parallel and returns a list of completed futures containing each task's respective successful or exceptional result. T-list future less than T execute all list callable less than T tasks, throws interrupted exception, try, var scope equals new structured task scope dot shutdown on failure. List less than extend supplier future less than T futures equals tasks dot stream map task greater than as future task, map scope fork to list, scope dot join, return futures dot stream. Map supplier get. 2. List. Static T callable future less than T as future callable less than T task. Return, greater than, try, return completable future dot completed future task dot call, catch, exception X. Return completable future dot failed future X. Custom shutdown policies. Structured task scope can be extended, and its protected handle complete method overridden, to implement policies other than those of shutdown on success and shutdown on failure. A subclass can, for example, 1. Collect the results of subtasks that complete successfully and ignore subtasks that fail. 2. Collect exceptions when subtasks fail, or 3. Invoke the shutdown method to shut down and cause join to wake up when some condition arises. When a subtask completes, even after shutdown has been called, it is reported to the handle complete method as a subtask. Public sealed interface subtask less than T extends supplier less than T, enum state, success, failed, unavailable state, callable less than extends T task, T get, throwable exception. The handle complete method is called for subtasks that have completed either successfully, the success state, or unsuccessfully, the failed state, before shutdown has been called. The get method can only be called if the subtask is in the success state, and the exception method can only be called if the subtask is in the failed state. Calling get or exception in other situations will cause them to throw an illegal state exception. The unavailable state indicates one of the following: 1. The subtask was forked but has not yet completed. 2. The subtask completed after shutdown, or 3. The subtask was forked after shutdown and has therefore not started. The handle complete method is never called for a subtask in the unavailable state. A subclass will typically define methods to make available results, state, or other outcome to code that executes after the join method returns. A subclass that collects results and ignores subtasks that fail can define a method that returns a collection of results. A subclass that implements a policy to shut down when a subtask fails may define a method to get the exception of the first subtask to fail. Here is an example of a structured task scope subclass that collects the results of subtasks that complete successfully. It defines the method results to be used by the main task to retrieve the results. Class myScope less than T extends structured task scope less than T. Private final queue less than T results equals new concurrent, linked, queue. My, scope, supernull, thread dot of virtual. Factory, at override. Protected void handle complete subtask less than extends T subtask, if, subtask.state equals subtask.state.success, results.add subtask.get. At override. Public myScope less than T join throws interrupted exception, super.join, return this. / returns a stream of results from the subtasks that completed successfully. Public stream less than T results, super.ensure owner and joined, return results.stream. This custom policy can be used like so. T list less than T all successful list callable less than T tasks, throws interrupted exception, try, var scope equals new myScope less than T, 4, var task, tasks, scope.fork task, return scope.join results. 2. List. For NEAN scenarios, the examples above focused on fan-out scenarios, which manage multiple concurrent outgoing I/O operations. Structured task scope is also useful in FNEAN scenarios, which manage multiple concurrent incoming I/O operations. In such scenarios, we typically create an unknown number of subtasks in response to incoming requests. Here is an example of a server that forks subtasks to handle incoming connections inside a structured task scope. Void serve server socket throws I/O exception, interrupted exception, try, var scope equals new structured task scope void, try, while true. Var socket equals server socket.accept, scope.fork, greater than handle socket. Finally, / if there's been an error or we're interrupted, we stop accepting. Scope.shutdown, / close all active connections. Scope.join. From the perspective of concurrency, this scenario is different not so much in the direction of requests, but in the duration and number of tasks. Here, unlike the previous examples, the scope's owner is unbounded in its duration, it will stop only when it is interrupted. The number of subtasks is also unknown, since they are forked dynamically in response to external events. All of the connection handling subtasks are created within the scope, so it is easy to see their purpose in a thread dump, which will display them as children of the scope's owner. It is also easy to shut down the entire service as a unit. Observability. We extend the new JSON thread dump format added by JEP 444 to show structured task scopes grouping of threads into a hierarchy. $JCMD PID thread.dump _to file format equals JSON file. The JSON object for each scope contains an array of the threads forked in the scope, together with their stack traces. The owning thread of a scope will typically be blocked in a join method waiting for subtasks to complete. The thread dump makes it easy to see what the subtasks threads are doing by showing the tree hierarchy imposed by structured concurrency. The JSON object for a scope also has a reference to its parent so that the structure of the program can be reconstituted from the dump. The com.sun.management.hotspot.diagnostics.spin API can also be used to generate such thread dumps, either directly or indirectly via the platform Bean server and a local or remote JMX tool. Why doesn't fork return a future? When the structured task scope API was incubating, the fork method returned a future. This provided a sense of familiarity by making fork resemble the existing executor service :submit method. However, given that structured task scope is intended to be used differently from executor service, in a structured way, as described above, the use of future brought more confusion than clarity. 1. The familiar use of future involves calling its get method, which blocks until a result is available. But in the context of structured task scope, using future in this way is not only discouraged but is counterproductive. Structured future objects should be queried only after join returns, at which point they are known to be completed or cancelled, and the method that should be used is not the familiar get but rather the newly introduced result now, which never blocks. 2. Some developers wondered why fork did not return more capable completable future objects instead. Since the future returned by fork should only be used after it is known to have completed, completable future would have offered no benefit since its advanced features are helpful only for uncompleted futures. In addition, completable future is designed for the asynchronous programming paradigm, whereas structured task scope encourages the blocking paradigm. Future and completable future are, in short, designed to offer degrees of freedom that are counterproductive in structured concurrency. 3. Structured concurrency is about treating multiple tasks running in different threads as a single unit of work, whereas future is mostly useful when treating multiple tasks as individual tasks. A scope should block only once to await its subtasks' results, and it should then process exceptions centrally. In the vast majority of cases, therefore, the only method that should be called on a future returned from fork was result now. This was a marked change from the ordinary use of future, and the future interface served as a distraction from its proper use in this context. In the current API, subtask: get behaves exactly as future: result now did when the API was incubating. Alternatives: 1. Enhance the executor service interface. We prototyped an implementation of this interface that always enforces structure and restricts which threads can submit tasks. However, we found it to be problematic because most uses of executor service, and its parent interface executor, in the JDK and in the ecosystem are not structured. Reusing the same API for a far more restricted concept is bound to cause confusion. For example, passing a structured executor service instance to existing methods that accept this type will be all but certain to throw exceptions in most situations.